All right. Thank you very much, Marcus. Oh, something is not working anymore. All right. Maybe I confused the many presenters here. Okay, I might have to do this by hand then. All right. So thank you very much, Marcus, for the introduction. Thank you very much, Marcus, and all the other organizers for giving me the opportunity to present our work here and for organizing this excellent workshop. Yeah, I will be talking today about oh, well, whatever. So this is yours now. Let's not confuse them. This one or mine. All right. So so thank you very much for organizing this excellent workshop so far. And I would like to talk today about fermions with an additional flavor, meaning that we want to use alkaline earth atoms here to implement an orbital degree of freedom and be able to do two-orbital physics with fermionic cold atoms. And the outline of the talk is that I want to quickly explain. Now, some of this has already been said, so I'm sure many of you know it, but quickly explain what I mean by this. What is the motivation and what is this two-orbital system, in particular with spin exchange. Then talk about how we can achieve really this system that we want to have that combines a spin exchange interaction with a state-dependent lattice and that can even be tunable. And finally, hopefully I will have time to shortly break out of the conference title of fermions in lattices and follow Martin's precedent and talk about general interacting gases, which is what we've been doing recently for quite a while without lattices. Yeah, explain what that is about. All right. So firstly, what do we want to do? What do we want to achieve with orbital? What do we mean by orbital physics? The optical lattices. Well, the idea is very simply illustrated by, let's say, for example, the desire to emulate something like the Kondo model, where you have electrons in the normal Kondo model, electrons of two types, or in general spins of two types, some that are localized and cannot move and are localized to certain locations, usually then for the normal Kondo model defects in the crystal, and the other spins which are electrons which can move around and are mobile particles inside the bands of this metal, for example. And we want to implement that, and in a similar way, by choosing alkaline earth atoms because they have two stable states, and you've seen that before very spectacularly in Journier's talk with the two states that he uses to drive the clock transition between, where of course the excited state is very long-lived. And so what we do is we essentially use the excited state of this clock transition to signify one orbital, and this then is subjected to a lattice which is selective and much more strongly confines this excited state than it does confine the ground state. So that means effectively that now these excited state atoms on this transition are localized, and the ground state atoms see a much weaker potential by choosing the correct wavelength of light and stay mobile. And then ideally this implements something like this Kondo Hamiltonian, which is a very simple Hamiltonian, which simply only has motion of the particles inside the mobile band. In addition has an exchange interaction term of the mobile particles with the localized particles and nothing else. And of course the important parameter and the new thing about this is here the spin exchange parameter of this spin exchange term. So this is now the idea of this classical Kondo effect, where I have single localized impurities that are in certain locations, and then particles, the other spins that are moving around can scatter off those. But there's another way of thinking about this, which is where we put a regular array of many of these impurities, which then no longer are impurities, and now have basically crystal of these localized spins, and that would be then the Kondo lattice model. It has exactly the same Hamiltonian for our purposes, but now we have an array of excited states atoms in this lattice, in this very simple type of implementation discussed here. And this is also a very interesting system, and as you can see here are some example phase diagrams for certain parameters, where the system has quite a complex phase diagram of many phases, both for the case where the exchange parameter is antiferromagnet, antiferromagnetic, such as here, or where the fundamental interaction is a ferromagnetic interaction, as shown in this phase diagram for the ferromagnetic case. So another motivation is to be able to implement this Kondo lattice model. And of course, there have been quite a few proposals to do this, and Anna Maria Rey is here, who initiated quite a lot of the important ones to look into the system with cold atoms of this type quite some while ago now. Okay, so, no, like this. Okay, so now going back, and this is now connecting directly to Jun's talk earlier. What about this important interaction parameter, this spin exchange interaction? How do we find it? And how can we measure it? And our method of choice, and this will show up many times, so that's why I'm showing this in detail on the slide, is a spectroscopic method where we do interaction spectroscopy on the clock line, or clock line spectroscopy, where that allows us to characterize the interactions very precisely. And you've seen that already in Jun's talk very shortly. Actually, I should make the disclaimer here that assuming that Jun is in the room somewhere, whenever I say clock, you should mentally add some quotation marks around it, because our clock laser is nothing like Jun's clock laser, which is absolutely incredible. This is more or less driving the transition a few orders of magnitude less coherent than what he's been talking about. All right. Yeah, so basically, interactions inside a 3D optical lattice, such as the ones that we want to do the physics in, would be on-site. Yeah? And then in order to characterize those interactions, I have to now imagine two atoms, and in particular two atoms of the two different orbitals, blue and green, on one side. And then with fermionic symmetrization, of course, just like what Jun already said, there are two possible ways to anti-symmetrize the state. I can either have the antisymmetric superposition of the orbital degree of freedom, or the symmetric one, and then correspondingly the inverse for the nuclear spin degree of freedom. And this gives me two different interacting states, which we call EG plus and EG minus, according to the orbital superposition. And these, in general, have two different interaction strengths. And we find those essentially by driving the transition from the ground state with the ground state interaction that we know, and then measuring the interaction shift relative to the non-interacting clock transition, or relative to the just ground state shifted clock transition, to find out the energy of these excited states. And then the spectrum would look like this, where we have the single particle peaks here, Zeeman shifted, and then there would be additional peaks coming up in the center due to interaction terms between the excited state ground state atoms and excited state atoms. And this allows us to very precisely find the on-site interactions of these channels. So yeah, what does this have to do with spin exchange? Many people it's clear, but to illustrate, this can be shown very simply in the context of this Kondo model. Yeah? If I imagine I have two particles that sit on adjacent sides, and now I have a tunnel coupling between the sides. Now, the mobile particle, the blue one, can tunnel to the side that has the localized spin on it. And now, depending on which of the two states it tunnels into, it will have an interaction shift that will be one of two different possible values. And now, after a while, this particle might tunnel out again. And of course, in the meantime, it was, in the general case, in a superposition between the two possible interaction eigenstates. And so there will be some phase shift that occurred during the time of evolution. And depending on the phase shift that will occur, the particle can now either tunnel back into the same spin configuration as before, or the phase shift can now lead to a 180-degree shift, which will then mean that the spins have now been exchanged, because now maybe I have gone from the symmetric superposition of the plus and the minus state to the antisymmetric, and then my spin down-up configuration has now changed to the spin up-down configuration. So that's the spin exchange we are talking about here. And now, in particular, that means, as you can see very easily from this model, that the spin exchange strength depends on the difference between these two interaction values, interaction energies, and antiferromagnetic or ferromagnetic depends on the sign of this difference. In this particular model, we were assuming that T is small compared to U. You can make a similar argument about also in the other case. And what then turns out to be the case for our earlier experiments here with Ytterbium 173 is that the UEG plus is much larger than UEG minus. So we have a very strong exchange interaction for this isotope, and it's strongly ferromagnetic. And we could estimate that this scattering length of AEG plus is larger than at least 1500 A Bohr. And that, of course, implies, as most of you will know, such a large scattering length that there's some resonance scattering going on in this plus channel. There must be a very shallow energy, weakly bound state. And then that then, of course, implies that maybe this is somehow analogous to what we have in alkali systems with Feshbach resonant states in interaction. So bound states that lead to Feshbach resonances in interactions. So then very quickly, after realizing this, there were proposals coming out from Peng Zhang's and Hui Zai's group in Beijing that speculated that there should be, or deduced that there should be, a Feshbach resonance very similar to alkali-type Feshbach resonances, but of a slightly different structure, which they called Orbital Feshbach resonance. And of course, this Feshbach resonance lives from the fact that we have two different interacting pair states that are called open and closed channel then, and one of them has this bound state, and I need some kind of mechanism to tune the bound state, in particular here, the one that is not connected to the open channel, so in the closed channel, into energetic resonance with the open channel energy for particles which are far apart. So this probably all of you have seen at some point. This is the usual diagram for Feshbach resonance. In order to somewhat illustrate this the difference between this normal Feshbach resonance image and this presumed orbital Feshbach resonance image, we draw this in a slightly different way, because basically in our case the interaction potentials are not particularly impressed by magnetic fields, because there's essentially zero difference in the magnetic moment, so nothing really moves around much here. So instead we draw it in such a way that now we have the open and closed channels which are split and moved around by a differential magnetic moment between the two spin configurations up, down, and down, up of these two pairs with one excited and one ground state atom in the system. Okay, and now the trick is that bringing the lower one into resonance with the bound state will lead to the Feshbach resonance. Okay, so that was the prediction. We looked, then started looking at this, not just us, but with the method that I just showed, what would we expect then? Well, now we have these two particles in one lattice side, and it's very easy to compute the energy shift that you would expect to get there as long as the scattering lengths are small. In our case now, one of these scattering lengths is very large, so then you need to be a little bit more careful and take into account that the wave function of the two particle state will be affected by the interaction itself, so you can't just take the Wannier functions and integrate. But this is a well understood problem, at least for the harmonic oscillator. There's a famous paper by Thomas Busch where they show the analytic solution of this problem, and then the energy that depends, the energy now of the on-site two-particle state here depends on the scattering length, no longer linearly. That's basically the region here in the center, close to zero. But as the interaction becomes large and becomes comparable to the harmonic oscillator length, it starts to level off, and you get a hybridized energy between the band structure and the interaction term. And this is somewhat what you expect then for harmonic oscillator as a function of the scattering length. And now if you use that, such a kind of model, and adapt it to our system of these two interacting channels, and convert it to magnetic field energy, magnetic field values rather than scattering length across a Feshbach resonance, then you get a diagram like this. So this is basically the blue lines computing the energies that we would expect in our situation, now as a function of magnetic field, not scattering length. And then take the data of the clock shifts, which are the points here. Then you can verify that this is indeed the case. And you can very precisely extract the interaction energies and the scattering lengths of the two interaction channels here. And we found something like 1900 and 220 A Bohr for these two channels. And this, again, has a very large difference. And this gives us this strong exchange interaction between the excited and the ground state spins. Okay, so that is basically now the fundamental interaction between the two orbitals in this 173 isotope. Of course, in order to scan a phase diagram, we want to tune this value also to different values. So there were immediately, and already before measurements were done, there were proposals on how to then tune this presumed exchange interaction value, and there's a variety of things you can do. Obviously, you can try to change the wave function overlap, to change the strength of the interaction parameter in the Hubbard model. And then there have been later proposals, for example, from the Demler group here, that it would be possible to tune the exchange interaction via some periodic modulations of either optical or magnetic fields. And in addition to that, they found that if you actually look at the biased system, effectively with magnetic fields and Fermi surfaces, then actually even in the ferromagnetic case, the system will tend to evolve towards an antiferromagnetic many-particle state, which is quite interesting and was at least surprising to me. But also then, based on the fact that we have such a resonant interaction, there was a proposal, again from the Zhang group in Beijing, to actually use something like confinement-induced resonances on this large channel to tune the exchange interaction rather than the open-closed, open-channel interaction that we have in the Feshbach resonance, but now use a confinement-induced resonance to tune the exchange value itself. And this is going to be relevant to a later part of this talk, where basically now we're looking at the combination, confinement-induced resonance here, a combination of an interaction channel together with the confinement of the optical potential again. Okay, so that's kind of what we'd like to do. And so now let's go and implement that. And so we want to bring these components now together experimentally, where that we have, first of all, we have these state-dependent lattice potentials where we have localized atoms and atoms that can move around on the one hand, and now marry this with the spin exchange interaction process in the same type of system that allows to flip spins between these two types of atoms, or two states of the atom. And how do we implement this? This is a very crude sketch of our setup. So we have a 3D lattice setup, which is essentially a lattice setup that's pretty much the same as what Junyi showed, with these so-called magic lattices on two axes. But on the third axis, we do something that is very horrible for the clocks. We choose the state-dependent lattice, which is exactly the opposite of magic, in the sense that it has a much stronger light shift, a much stronger confinement for the excited state atoms. And this is now this longitudinal direction along these tubes, and we can vary the intensity along that axis, whereas the transverse lattice is usually more or less constant at some constant value, and just separates all the system into independent tubes here. And in addition, along the transverse axis, we have the clock laser, or what we call the clock laser, that couples the excited and the ground state and allows us to do the spectroscopy and to prepare the state in the E and G mixture. Okay, now going back to what we looked at before, how do we understand this new system now? Again, we have a 3D lattice now with two normal magic harmonic oscillator axes and one of these state-dependent axes now. So what changes? In our model before, we have to plug in some of these things. One thing, for example, is that immediately changes is the anisotropy of the sides. Now we have the strong confinement along the transverse axis, and in the longitudinal axis we have, in general, a less strong confinement. And in particular, it's also a different confinement for the E and G atoms. So we need to modify this Bush model now. And the anisotropy basically gives us a bit of deformations here in these Bush results. But and energy shifts basically. Now, if we, in addition, now plug in anharmonicity effects, because our lattices are not that deep that the harmonic oscillator is a perfect approximation, and in addition include the state dependence of this lattice potentials, then we get a very strong coupling also of the relative motion of the two particles and the center of mass motion of the two particles. And what I showed you before was essentially just the results of the relative motions of the two particles, removing all the center of mass motion, because in the Bush model that doesn't really matter. You get for each center of mass motion vibrational quanta, you get the same result. It's just a different set of states. In this case, due to the center of mass relative motion coupling, this is no longer the case. So now we have to take these additional states into account. These are the dashed lines. So essentially for every relative center, relative motion solution, we have a family of center of mass excited states that come in now and are coupled to the non-excited one via the potentials. And yeah, so this changes the energies and the structure of the spectrum a little bit. And also we want to now probe this in a different way. We want to probe the system in such a way that we actually look at the spin exchange. So we want to watch it, watch the spin move from one orbital to another. And so in addition to the spectroscopy, we can do a different type of experiment, which is where we prepare all the particles on separate sites. Yeah? So there are no prepared pairs. And the ground state atoms are all in the upspin, and the excited state orbital is all in the downspin in this initial preparation. And then we quench the system and allow mobility by a magnetic field and reducing the lattice depth. And then we just wait and look at the time evolution of this highly non-equilibrium initial state. And then basically for the simple most experiment would be to just count the spin components and see how the populations evolve. Now, what is the model here? The model that we are thinking about here is, again, similar to what I showed you before, where we consider that now we actually only do a Kondo impurity type system with a minority of the atoms being in the excited state orbital, in the localized orbital. And so since we start with individual atoms on sites, the spin exchange process has to happen the way I showed it earlier. I have to have one particle tunnel to a localized particle on another site and then tunnel back, and this constitutes the total spin exchange. Of course, if the tunneling is weak, and this is typically the regime we are in, this is going to be a detuned process, so really the entire process is going to be a second order exchange interaction process leading directly from this state to that state or staying in that state. Now, energetically, for our interactions that we figured out, it will of course look like this. Yeah? We have the U minus state here and the U plus state, which has this very strong repulsive energy at a much higher energy. So now the dominant spin exchange process will be the one where you go via this virtual state, the triplet U minus state. And because this is the triplet state, it means that this exchange interaction from here to there is ferromagnetic in the end. Okay, so this is what we would expect. And we can compute basically using this U minus value and the known T value what kind of exchange interaction strength we would expect in this scenario. And that, of course, as a second order process, if we adiabatically eliminate the intermediate state, then we get something like Tg squared over U minus for the interaction strength in this scenario. Okay. And so indeed we get an spin relaxation process. Now if we count the number of excited state downspin atoms and compare to the excited state upspin atoms, of which we initially don't prepare, then we see that this state starts to be populated as a function of time via this exchange mechanism. So there's indeed some exchange happening. But there's something in addition that we see is that this exchange strength and the general behavior, surprisingly, depends very strongly on the transverse confinement. So what's shown here, these three different graphs, are the same experiment but for different strengths of the transverse confinement of the system, which is a bit puzzling because we were expecting, at this point, we would be expecting only T square over U, and the T only depends on the longitudinal lattice, not on the transverse. So if I extract some kind of interaction strength value, then we get a graph like this as a function of the transverse confinement. So this rate, this extracted rate now is actually very strongly dependent on the transverse confinement strength. No. Yes, we start with all spins down, and so this is just the excited state orbital. For the ground state orbital, it's the other way around. So we expect the spin to be equilibrated between the ground and the excited state orbital, right? So the total spin is not fully polarized initially. For these experiments, I'm not 100% sure. For the next slide, it's actually more or less 50-50, but the density is not super high. So it's not like a Mott insulator. So it's a relatively high density here. So because we're basically only counting.
Why are the number of upspins plus the number of downspins not conserved?
Right. So in addition, obviously, in this particular parameter regime, there's actually loss of the particles. I'll get back to that in a moment. So, and in particular, that loss is very high, close to this apparent resonance structure here, where suddenly the exchange strength becomes very large. And I should point out that the computed value would actually be more or less this one down here, around 15. But we suddenly get these very high values for certain combinations of potential strength. Yeah. Okay. No more question. All right. So it turns out that this is not only dependent. This behavior not only depends strongly on the transverse interaction strength, but also the longitudinal one. And if we vary both, we get this funny resonance structure where for certain combinations of lattice depth and longitudinal and transverse direction, we get these exchange resonances. Now what's plotted here is something like effectively the rate, the exchange population after a certain point in time, at a certain point in time, effectively the rate of exchange for that set of parameters. And now that was one of several things that puzzled us initially, but it actually becomes reasonably understandable if you start to think about really now, if you this confinement-induced resonance type picture, or take into account what I said earlier, that we now have to modify the simple Bush model, and we have to take this relative motion, center of mass motion into account. Because then you understand that you actually need to modify the simple image that I showed before as the fundamental process of the spin exchange. Yeah? So this was the picture that I showed before, but really, if you remember this, this Bush model plot, there were also these pair states at negative energies. And these also contribute in principle to the exchange process. And in particular, there's this bound state, the one that's causing, effectively the one that's causing the resonance in the first place, that has negative energy as a bound state, and that is a singlet state. And so this path actually also contributes to the exchange process. So normally, this bound state energy is something like 20 kilohertz in this scenario. So it's actually also very far detuned to this to the non-interacting scenario, to the open channel, if you want. So therefore, it contributes only very little. And what we would expect is somehow the total spin exchange is the sum of these two channels, effectively. But as it turns out, then of course, with the center of mass excitation coupling, we can actually have excited state, confinement-induced resonance states, if you want, that the system couples to. And now these states are basically center of mass excited copies of the bound state pair. And these can now come into resonance with the open channel, because their energy, of course, depends now on the energy of the bound state singlet, which in turn depends on the lattice parameters. And also the spacing here depends on the lattice parameters, in particular the longitudinal one. And therefore, I can tune these guys up and down, and this leads to resonances whenever one of those states crosses the open channel. Yeah? And then if I plot this is a crude calculation that we did, where the red curves are now these channels of concern. And if I plot this into this diagram, then at least qualitatively, it kind of matches what we see in terms of this resonance structure. And in particular, if you compute what's happening here, is that, of course, this is really like a resonance scattering process. So we have zero crossings, and we also have the divergence in the center. And in fact, even the sign of the interaction that you compute out of this changes close to this resonance. So you can even flip it from ferro to antiferro and back. But on the other hand, of course, and we talked about this earlier, this being a resonant process, it also leads to additional losses. So there's a limit on how close one can operate to these resonances in order to avoid additional losses via this bound state decay. Right, but it's definitely a way to modulate the strength of the interaction on top of the other methods shown. Right. Okay. So there's also another way, another fairly recent way to tune the interaction, the exchange interaction, which is by essentially varying the number of neutrons in the atom, and by flipping the isotope. And Ytterbium has two fermionic isotopes, so two that can be used for this type of physics. We have been using 173 isotopes so far, but a while ago, like last year, we've started to prepare to also be able to cool Ytterbium 171, which is harder because it has no ground state interaction. So you have to basically cool it in a more complicated way, sympathetically with something else. But then in principle it has its own interaction properties, and then if you manage to do that, which finally we did a couple of weeks ago, then you can do the same type of experiment there, and if you do the clock line spectroscopy there, it turns out that you also get very nice interaction resonances, and if we analyze those, and we do this by varying the magnetic field and looking at the field dependence, then we find out that this isotope also has an exchange interaction, and in that case, by fitting the very simple model that gives us these values, we find interaction strengths that are of intermediate height, like 230 and 370 approximately a Bohr for the two interaction channels. So there's a difference of 140 a Bohr that gives us an exchange, and it seems to be antiferromagnetic for this particular isotope. So gives us a starting point now on the other side of the resonance as well for the other isotope. Right, and I should point out that you will probably hear about this again by Yoshiro Takahashi there. So their group has measured this also, and they put a paper out last week, also looking at this isotope and their exchange interaction a couple of weeks or months back. Okay, so then in the last few minutes, as I said, I would like to very quickly say something about something we spent a lot of time with recently, which is switching off two of our lattice axes and looking at the bulk system that remains in the remaining 2D type confinement in these pancakes that you get inside a standing wave, and now exploiting essentially the Feshbach resonance more or less like a alkali metal Feshbach resonance, and looking at the similar type of phenomena there, now with the added flavor of having basically the special Feshbach resonance, which in the quantitative analysis shows up that you need to take the two channels into account. So what happens, I mean, I don't have to say much about this because Martin already explained this much more detail, much better than I could. But yeah, what we do is we put atoms, in our case, in a 2D system into these pancakes, and then prepare an impurity. So initially all in one state, in one orbital, and then we inject again impurities now with different, in a different state, in our case the excited state orbital, into the system, and look how this behaves, and expect to see the Polaronic type of physics, similar to what Martin explained, but now in the two-dimensional variant. Yeah, so I don't need to explain much about the system, so we simply have a standing wave with a confinement now that is very strong, and the harmonic oscillator in this case is comparable to the scattering length in this resonant channel, so we can tune quite far around with this Feshbach resonance the strength of the effective interaction. And what we prepare is initially a mixture of spin up and down atoms in the ground state, and the down atoms are a minority in this preparation, and then we excite them to the excited state, and get basically now impurities of excited state atoms that can strongly interact in this particular spin mixture, which gives us this Feshbach resonance behavior. Okay. What do we expect? Well, we already heard about this. There's a number of things that can happen with these pair. We could be in a situation where we could, of course, form dimers, so essentially molecules in that process, which would then basically be more or less two-particle physics, depending on the environment. But we could also be in a situation where we have attractive or repulsive Polaron, similar to the scenario that Martin described. And we looked at the different regimes, and this is still a bit of ongoing work. We can identify the dimer if we tune the system now. This is at a somewhat lower density in order to be able to separate this. We can find a dimer channel here, and extract the energy of this bound state now as a function effectively. So this is Lz over A3D, so the scattering length in 3D, the regular scattering length, and compare this to what we expect for the bound state in a 2D Polaron or a 2D dimer scenario, and you see basically the crossover nicely from the effective 2D scenario to the 3D bound state for stronger binding energy of the bound state system. But more importantly, we can also go to the Polaron system now, really where we have a high density and an impurity scenario, and do this injection spectroscopy directly while at fixed energies, basically. So what we do is we prepare now this impurity at a certain energy by tuning the frequency of the excitation laser. And this is the kind of spectrum that we get, and it looks very similar to what, as expected, very similar to what people see in the alkali system, which we found very nice. It took us a while to figure out at which point it's not only good looking, but also well controlled. But we think we understand this reasonably well, so we get a this would be the non-interacting state, so we get a repulsive and an attractive Polaron branch. The particularity of this Feshbach resonance is that we can't go very far to weakly interacting repulsive side because simply the magnetic field runs out. The magnetic field zero happens there, so we can only look into this intermediate range of interactions. And so what we can do is we can excite into this Polaronic state. So this is a couple of examples to look at the lifetime. And this is the kind of experiment that we saw earlier. Also in Giacomo actually talked a lot about how to analyze these in a professional way. This is somewhat similar along the lines of what they did to understand the lifetimes. This is the lifetime of the excited atom itself. So it shows the rate of decay into the attractive Polaron and decay into dimers. And what you can see here is also that the lifetimes are significantly longer than the Fermi energy scale. So this is given by so this is the lifetime plotted now as a function of KFA 2D. So this is now the 2D scattering length, the effective 2D scattering length. And you can see that the lifetime is now dependent on this interaction parameter. And they are all the decay rate. So sorry, this is the decay rate, not the lifetime. The decay rate is significantly slower than the Fermi energy, so this is a well-defined quasi-particle. But in addition, we also have this effect that I think Martin mentioned, where you have the decoherence of this Polaron due to collisions due to collisions with other particles, which is on the scale of the Fermi energy, or depending on the interaction. And so we also see this type of behavior in a similar way. So this is where we started to analyze that, where we drive coherent coupling between the ground state and this Polaron, where we can see a couple of Rabi cycles, and depending on where we are in this diagram, as you can see, it both becomes slower due to the reduction of the wave function overlap between the free particle and the Polaron state, and the coherence goes down as a function of this decoherence due to collisions there. Okay, so now finally, this was motivated by several people pointing out that this could be an interesting system because this Polaron now, in order to describe this correctly, you actually, to be really quantitatively correct, you need to take into account that now you have actually these two channels present at the same time, because the binding energy of this bound state is relatively low and not so far away from the Fermi energy. So it effectively means that you always populate the other channel to a much higher degree than what you would otherwise do. And you can modify the system by actually actively populating that channel in our case, because we can put atoms now not just into this up state here that strongly interacts, but we can also populate the other state, which kind of modifies the system in the sense that now the virtual spin exchange to the other state, the virtual spin exchange process that is always present in the systems as a function of the magnetic field, is blocked, and this should modify the interaction or the properties of the system. And there's a couple of predictions of what should happen. We are trying to find one that is something that we can probe easily here. It should, for example, change the interaction, the energies of the polarons, and it should, in principle, also change things like the lifetime. And we're trying to understand how that actually works. Okay, so I'm running out of time. So finally, I should point out the people who did all this work. So this was the current team on the Ytterbium experiment, and with Nelson and Oscar doing most of the Polaron work, Julian Lewis working on the exchange experiments together with all the other guys. And so yeah, thank you very much for your attention. Mm-hmm. Yeah. Yes. Well, yeah. The way I show this. Okay, so the question was why is the relaxation a relaxation, and why is there never any coherent oscillation process happening between the spin exchange, which could in principle go back and forth. The way it's shown here usually is a bit misleading in that I always show two sides, right? But in reality, it's not a system of only two sides, but the particles move around also at the same time, and there's also the additional confinement. And so really, in order to compute the correct dynamics, we have to basically take into account that the ground state particles are also delocalized, so they're inside the band. And so there's an energy spread also in different, or if you want to have a local picture, you can also take into account that on the sides of the cloud, you have the gradient between the two sides that also affects the effective coupling strength. So we don't expect actually there to be a well-defined frequency where there would be a coherent interaction, because it's really a gas of many particles and they kind of collide and exchange.
So going back to this two-channel super exchange that you saw, so I understand that if I start from a one-particle per site system and I let the super exchange happen, it just renormalizes the super exchange and can change its sign. Right, but if I now actually look towards the many-body ground state or something, it seems like it would have a really drastic effect. Things might want to sit in this attractive bound state instead of being a mod insulator, for example. Have you thought at all about this?
Okay, now first part, yes. The second part, I'm not sure what you're implying.
A bound state that's it's below zero energy, right? So
yes.
If I cool the ground state of the system, it's not going to look like a mod insulator. Presumably, you have a bunch of doublons floating around because it actually is favorable in energy. Or am I thinking about this a little bit wrong?
Okay, yeah, the fact that there's the ground state will lead to a decay through this, into and through this ground state. And depending on which system we are looking at, this is not necessarily a state that we want to have populated, so that would then be a problem. This in particular happens close to these resonances because there the coupling to these bound states is strong. And basically they can then de-excite via collisions with yet more particles. So normally for the physics, like for the Kondo physics that I showed, with outside of these resonances, this bound state is not supposed to be involved, let's say, other than affecting the interaction properties. Yeah.
Beautiful results. On the Fermi Polaron part of the talk, I was wondering, so this injection spectroscopy is of course great to see all the possible excited states, including the repulsive Polaron, but now to see the ground state of the system in the strong interacting regime, where maybe the quasi-particle wave is kind of small, you want to probably prepare the ground state and go into the non-interacting system with your spectroscopy, so do ejection.
Mm-hmm.
Is there some problem doing that, or could you just do that too?
It's somewhat harder because we have to then prepare the system with excited state atoms around, and if we want to do that adiabatically, that we have to do that slowly, and lots of excited state atoms are not terribly stable because collisions between them are lossy. So we have to do that at very low densities and make sure that they basically don't meet, which makes this indeed harder. Also, what we do not have in this scenario is what you guys have, these very nice, very weakly interacting, or in some, at least some alkali atoms, very weakly interacting states. So when we do the spectroscopy, we also always have to take into account the final state energy in addition. But in principle, yes. So, but what we have tried a little bit is similar to what I think Giacomo showed, where we inject and then you time evolve and you look at what happens then. And we also see that basically the energy, the system relaxes a little bit. For us, the effect is maybe not as strong because the energy spread is not as big as for them. But this is the type of non-equilibrium. If you want, we can do that. Yes.
This goes back to the question that was asked earlier. If you have one polarized impurity spin and the Fermi C, which is also polarized,
Mm-hmm.
and you ask, okay, is my relaxation just relaxation, and does it have oscillation? I think in this extreme case of strongly polarized system, you do find oscillations even in the membrane problem.
Yes, I would expect that. I would assume that it needs to be very homogeneous for that. So.
I think even in problem we just have random couplings. Surprisingly, you still have.
With random couplings. Okay. Okay, so that would be then on the order of Fermi energy oscillations there, or how would that become
so if it's homogeneous coupling, then
normalized?
it's easy to get the scale because it's okay. It's a long story. I think it's still of the order like this J.
Okay. Okay. But yeah, okay. Of course, we do have always the inhomogeneous Fermi energy also on top of this, right? So which,
Would this give you
but
homogeneity?
it would probably dephase on some degree. Pardon?
Would this give you homogeneity of J?
No, not of J. That's what I'm saying. Of Fermi, of the Fermi energy.
So one last brief question, Amelia.
But we should discuss that.
So in the pancakes, for example, in the clock, we have a very important contributions from P-wave interactions.
Mhm.
Are very cold that you don't see them, or do you see any contributions from P-wave?
Okay, we have not spent humongous time on searching specifically for P-wave, but we can say for sure that they're much, much weaker than the S-wave interaction. Oh, you mean for the polarized case in particular? So, well, in the pancakes, I mean, it's still a mixture, so we're interested in the EG interactions. So, yeah, even so, we do drive polarized, and it's compatible within our precision that we have looked at so far with no P-wave interactions on the energy scales that are important for us for this isotope. So that, I mean, just happens to be the case. Say again? The temperature. Well, we start usually here for this. We start usually with T over TF temperatures, 0.2 or so coming in from the dipole trap, and then loading into the pancake.
Yeah, good. And let's thank Simon again.
Thank you.